First, I'd like to thank the organizers for organizing this wonderful workshop and for giving me this opportunity to talk about my work with Luis Apollo and Stephen Diternay. And I will talk about TTbar, TST, and black screens. So over the past 20 years, we've learned a lot from the holographic duality between gravity in asymptotically ADS space and the conformal field theory living on the boundary. However, we don't really live in asymptotically ADS space, and to understand quantum gravity in our real world, it seems to be important to understand holography for example, Minkowski space, the theta space, and Kerr black holes. So today, I will describe a toy model for holography with whose bulk geometry is asymptotically flat. And I will describe this model from three corners. One is from this string worksheet perspective, and the second corner is from the bulk geometry, and the third corner is the dual field theory. So this model can be constructed from a known string ADS CFT model built from string theory. And it can be constructed using NS1 and NS5 branes and take the near horizon limit. And we know that near horizon has an ADS3 vector. And there is a CFT dual to this theory. On the other hand, this background has a weakly coupled string theory description described by this WZW model. So what are we going to do from these three descriptions? And how can we get a model of non-ADS holography from that? Well, from the CFT perspective, we will be doing the so-called TTbar deformation, which is an irrelevant deformation. It will, so the CFT is in the IR, and after this irrelevant deformation, we'll get a new UV theory. It is not necessarily, not necessarily, it's actually not a CFT anymore in the UV, and actually not necessarily a local quantum field theory. And from the string worksheet perspective, we will be doing a marginal deformation. And this deformation can be generated by the so-called Tst transformation. T corresponds to a T duality, and S is a shift, and T is another T duality. I will give more details later. And this is from the worksheet, it's a marginal deformation. From the dual CFT, it could be an irrelevant deformation. And the bulk geometry that is due to the deformed CFT is again can be obtained by a Tst transformation, and this will change the asymptotic boundary, and we will obtain some black string solutions which are not asymptotically ADS3. So this is the general structure of my talk. So I will first talk about the dual field theory corner. Namely, I will first describe what is the TTbar deformation and what properties it has. And then I will go to the string worksheet description. And then finally, I will talk about the bulk geometry. And
Wait, sorry. Are you still in the first page of the slide, or are you turning your slide?
I'm turning my slides. Can you see it?
No. We are still on the first page.
Oh, sorry. Can you?
Oh, yeah, we can see this.
I'm already on page 5.
No, somehow we couldn't see the other pages.
Oh, sorry. What am I going to do? Can you see it now?
Yeah. It's fine. This is fine.
Maybe I just make it bigger.
Yeah.
Sorry.
Okay. Yeah, it's fine.
No, it's fine.
Yeah. Thank you.
Okay. Sorry, this is the second page. And here is the, but we can directly go to this page 5. Can you see it now? This diagram. I have these 3 corners. The ADS3, CFT2, and WZW model are the 3 corners or 3 descriptions I was talking about before the deformation. And in the field series set, I will do a TTbar deformation, and that would lead to a new field theory. And on the worksheet, I will do a marginal deformation that would lead to a new string background. And the geometry will also be deformed, and it will be a new black string background, which is not asymptotically ADS3. Okay, so that's the plan. I will first talk about the TTbar deformation. Okay. So a TTbar deformation can be described by such a differential equation in terms of the deformed action. So this S mu is a dimensionful deformation parameter, and the deformed theory depends on the deformation parameter. And the action, we can take the derivative of the action with respect to the deformation parameter mu. And the result is actually the determinant of the stress tensor. Here, we are putting the theory on a circle, the 2-dimensional field theory on a cylinder, where T is the time direction and phi has a length, let's say, has a finite length R. And we can combine T and phi and to have 2 like-cone coordinates, that's called X and X bar. This TTbar deformation with this description is actually defined instantaneously. It can be is defined at any value of mu, of the deformation parameter mu. And people find that such a deformation, we can, putting on the cylinder, we can just derive the spectrum, the deformed spectrum, in terms of the deformation parameter mu, the length of the circle on the cylinder R, and the undeformed spectrum, namely the energy E and the angular momentum J. So because charge quantization, this angular momentum is not deformed, but the energy has this weird square root structure in terms of the undeformed spectrum. And for further convenience, I would like to write this deformation of Titivate in such a way using the two nodal current, namely J1 is the one form that corresponds to the translation symmetry along X, and the J2 is the translation symmetry for X bar. With these two nodal currents, we can very compactly write the action in terms of the wedge product of these two nodal currents. That will be a useful way to relate this dual field theory deformation and the string worship deformation, as we can see later. Okay, so this is this Titivate deformation, and we know the spectrum. But because of this square root there, we'll see that the sum of this deformation parameter mu matters. And in the case when this parameter mu is negative, we'll say that then there is an upper bound for the energy. Above the upper bound, if E is too large, then what inside the square root will become negative, and the deformed spectrum will become complex. It's interesting to understand what will happen above this upper bound, and I think there is still, this question is still open. But for one can also observe that this the spectrum will become problematic at high energy, but for the ground state, it seems to be okay. The energy is still real. So one can also observe that the deformed spectrum, the energy level doesn't cross, so that we can suppose before the deformation, we are in the Cardi regime. Then after the deformation, we will know that how the density can be expressed in terms of the deformed energy. Namely, you can just rewrite the Cardi formula in terms of the deformed energy. So there are proposals for this Titivate deformation in 2 dimensions. This deformation, Titivate deformation, the holographic dual is proposed to be due to asymptotical ADS geometry in Einstein gravity, but with finite cutoff in the middle of the spacetime. This cutoff is related to the deformation parameter. One can also add this so-called lambda 2 deformation, and then the bulk geometry would become a patch of the theta space. There are also higher dimensional generalizations of this Titivate deformation, and again, the bulk proposal is also to impose some directly boundary condition in finite cutoff. There are also lower dimensional proposals. On the other hand, there's another choice of the sun, which is mu, this deformation parameter, is positive. Then by staring at this spectrum, one notices that at high energy, there's nothing wrong with this, while this energy is still real, except that this, if it is above certain value, the density of the states would look like a Hagedorn growth instead of this Cady behavior.
Can I ask a question?
Yes, please.
Well, in the previous page, you talk about this holography at finite cutoff.
Yes.
And at the cutoff surface, do we have a dynamical gravity, or it is just a fixed background?
This you just impose. You can have. So this TTbar is you can also understand it as imposing some boundary condition to the gravitons. So TTbar it's to impose directly boundary condition to the metric at finite cutoff. So you can also
on the cutoff surface. So the graviton is no longer dynamical.
Yes.
It should be a fixed background.
No, it's not a fixed background. It's just the metric are allowed to be anything except that it has to satisfy the directly boundary condition at the cutoff surface.
Okay. Okay. So the gravity is non-dynamical. That's what on the cutoff surface.
On the cutoff surface, yes, yeah.
Oh, okay. Okay. Thanks.
Yeah, in principle, one can also add matter, but then the TTbar is only to impose boundary condition for the graviton. If imposing directly boundary condition for other matter correspond to doing double trace like a similar deformation for the matter as well.
I also have a question. What is the definition of the TTbar deformation for higher dimension?
It's roughly speaking, it's the determinant for the stress tensor. So the right-hand side, the left-hand side is still this. The right-hand side is the determinant of the stress tensor.
So it's a higher power of T. More than here it's quadratic, but it's higher and higher. Oh, okay. Yeah.
Okay. Shall I continue? Okay. So yeah. So this the cutoff proposal is for this negative sign of the deformation parameter. Today I will mainly focus on the other sign with positive mu. It has different behavior from the other sign. So we see that the spectrum will not become complex at higher temperature is still real, except that it has hexagon behavior. On the other hand, it might become problematic at a very low temperature, at a very low energy, namely the background. Usually the ground state would have a negative negative energy, -C/24, or -C/12, 12. So if we plug that into this deformed energy, we'll see that if the deformation parameter is too large, namely this combination, this dimensionless combination of the deformation parameter is greater than a half, then the ground state energy after the deformation would become complex. So in this other same choice of the TTbar deformation, there is a critical value for the deformation parameter, and it's by some combination is the number of half. Relatedly, one can also talk about the temperature. The temperature can be derived from the entropy formula and the energy. So by some simple calculation, one can find that the temperature, the left moving temperature and the right moving temperature would have the product has an upper bound, and this upper bound is inversely proportional to the cutoff to the deformation parameter mu, and it's this relation. Then one would ask, what would be the holographic deal with this choice of the sun? The proposal, as I predicted, it comes from string theory constructions. We have, let's consider type 2B string theory on ADS3 cross S3 times some 4-dimensional internal manifold. And we have some NS fluxes, and we have basically K as 5 branes and P as 1 brane charges. So there is, on this background, there is a holographic, there is a proposal for the holographic duality. In particular, the long string sector of this theory is proposed to be a symmetric product, where this M6K is a SID CFP with central charge 6K, and P is the number of the NS1 branes. And you have the SID and you make P copies and doing the symmetric product. There are some evidence showing that the spectrum matches, and there's also some evidence for the correlation functions. In particular, at when K equals to 1, there are, it seems that there are more evidence for the proposal.
Wait.
Hello?
Can I ask a question? So in this proposal, right, the TTbar is a single trace deformation, right? I mean, so you have to sum over the symmetric orbifold copies, right?
Yes, I will talk about that later.
Okay. So my question is like whether it's possible. So whereas the previous case that you were discussing, right? I mean, when mu was negative, so that was a double trace deformation. So in this interpretation is a single trace deformation. So I was going to ask whether it's possible to have positive mu, but still like a double trace deformation. That
I don't know, because so for positive mu, I don't know if there is a double truth version.
I see. Okay.
Because it so for negative mu, you push the cutoff to the interior, but
Right.
if you change the sun, I don't know the picture.
I see. Okay. Thank you.
But for single trees, in fact, you can do both suns. Okay, so yes, then there is as I mentioned earlier, there's a third corner by using the WCW model, which is the worksheet string theory description. So then yes, before I was talking about this double twist deformation. Actually, a TTbar deformation, one can say that indeed it's by definition, it is a double twist deformation. Then you could ask me, what do you mean by a single twist TTbar deformation? So here it's defined as follows. So this before the deformation, we have a symmetric product. So actually, the single twist deformation of TTbar deformation is to do the double twist TTbar on the state theory, and then perform the symmetric product. So this way, there is a sum over the over this I. If we sum over the total action, there is a sum over I. But we see that the product, the two I's have the same index. Alternatively, one can consider doing the ordinary double twist TTbar deformation to this symmetric products CFT. That way, you would be summing over Ji and Jj, summing over I and J. So in that sense, this deformation is a single twist instead of a double twist deformation. That's the dual CFT set. We are doing such a deformation, namely we deform the seed CFT by a TTbar, and then do the symmetric product, and that defines the single twist deformation. And in the then one can ask what happens in the other two corners. So the space-time would be deformed to a asymptotic flat space with linear dilettone instead of still locally ADS space-time. So there are certain pieces of evidence that we can show. One is that one can consider the long string spectrum on this string background, and calculate the string spectrum and rate it in terms of the antiformed spectrum. And one can see very explicitly that this deformed spectrum indeed agrees with the TTbar deformation spectrum. One can also show that certain black holes can be constructed, and their thermodynamics can be matched to the TTbar deformed field theory. And moreover, one can actually show that this deformed geometry, you can actually construct most general non-rotating black hole background that correspond to the finite temperature excitations of the deformed the deformed field theory. So in
I have
particular,
a question. Can I ask a question? So here, the Titivate deformation, under this Titivate deformation, does the supersymmetry is preserved or no?
in general, it's broken.
Broken. I see. Thank you.
Yeah. Right. In general, these supersymmetry are broken. So what we more we found that actually this TTbar deformation can be realized by Tst transformations in the bulk. I think I'm going very slow. So I need to speed up. So here is a summary about this double trace and single trace deformation. There are more work on the double trace holography for the double trace deformations, and there's also this TTbar deformation. For single trace, it has to be, it's slightly less universal than the double trace deformation. We have to embed it into string theory. And but a main feature of the single trace deformation is that it changes the asymptotic geometry. This is very different from the double trace deformation. In that case, the bulk geometry is still ADS. It's just you will impose a different boundary condition. Okay, so much for the field theory set. Any questions?
Excuse me, please. Concerning your deformation parameter, has the dimension of curvature. Is it possible to express your action, which was written in terms of stress tensor, in terms of the curvature?
In terms of the curve, here I was talking about the field series on flat space.
Yes, but I am talking about the worldsheet definition of the action. This action includes in the worldsheet additional parameter which has dimension of curvature. And for example, if we consider the Nambu string model, we can add there a curvature like two-dimensional gravity. And the curvature of this worldsheet can be considered as a deformation parameter, which may be considered as constant, which you introduced.
The curvature of the worldsheet.
The curvature of the worldsheet, exactly.
Can be considered as a deformation of.
Sure. Sure.
I see. Sorry. Are you asking what's the relation between this curvature and the deformation I'm talking about?
Yes, that's right. I'm just talking. You are talking about the deformation of the standard Nambu action, which does not include parameter mu. But your parameter mu has a geometrical sense of curvature because its dimension coincides with dimension of the curvature. And it means that you can add to the action of Nambu some terms which, for example, proportional to curvature. And this curvature could be constant and can be considered as geometric deformation of the world sheet, but described in terms of curvature.
I don't know the relation at the moment. Maybe we can discuss later.
Yeah.
Thank you.
Yeah, thank you. I'm sorry to disturb you.
Thank you. So maybe let me go to the worksheet. So here is the before the deformation, the bosonic worksheet action. We have a background B field. Here G is the metric, the target space metric. We can add them up and form this matrix. We call it M. So we can perform. Suppose we have two global UN symmetry on the worksheet. That's denoted as translation along target space direction x1 and x2 bar. Then we can perform a Tst transformation. Namely, we do T duality along this x1 direction and shape the x2 with a parameter lambda tilde, and then do T duality along x1 again. This would lead to a new stream background, and after the deformation, we will have a new metric and background B field, and or alternatively, we have a new this M matrix. So that's denote the deformed M by M tilde, and one can say by simple the rules of T duality, one can derive that this the deformed M and the original M satisfy this matrix relation, where lambda tilde is a deformation parameter and is related to what I call the mu by some dimension for parameters. And the gamma is a matrix which pick up these two UN directions, x1 and x2 bar. So one can, the effect of TST is to change this M to M tilde. Using that, one can say that after this deformation, at any finite lambda tilde, one can perform this derivative of this M matrix with respect to this deformation parameter, and that would lead to such a differential equation for the deformed worksheet action. Interestingly, this worksheet action, when it take derivative with respect to lambda tilde, can also be written as the product of two UN currents. And these two UN currents are the corresponding Noether currents of these two translational symmetries on the worksheet. So namely, these are the worksheet Noether currents of this x1, J1 correspond to x1, and J2 bar correspond to this translation x2 bar. So then, if recall the definition of the TTbar deformation on the field theory set, it can also be written in a very similar form, namely the space-time or the dual field theory action take the derivative with respect to the deformation parameter is also the product of two nodal currents. And we have this the nodal currents on the worksheet and the nodal currents in this dual field theory. They have one-to-one correspondence. This is very they look very similar, and we have and it's they are the same translational symmetry, but written in different ways. One is on the worksheet and others in the field theory set. This is an observation, but it indicates that such a worksheet deformation could be due to this deformation on the dual field theory. Note that when these two directions, x1 and x2, are chosen as our two null directions, we can say that in the field theory set, the translation generator of the translation in these null directions are just the stress tensor, and it has dimension 2, and this is layer 4 becomes irrelevant deformation. But on the worksheet, these are all worksheet marginal deformations, because on the worksheet these symmetries all have a worksheet conformal weight 1, 0 and 0, 1. So this is an observation, but we can give some evidence. So one before giving the evidence, we can this Tst transformation actually has been discussed in the literature of this dipole deformation and non-relativistic deformation in other contexts. For example, in this TEMP 2B string theory on ADS5, with there you have R background, and there is already some evidence that such deformations, depending on this your choice of the U1 directions, they would correspond to this non-commutative deformation if the two U1s are chosen in your ADS direction, and if it is if they are both in the internal directions, you have the so-called beta deformation. If one in ADS, the other in the internal direction, you have this dipole deformation. But here, we would like to consider this ADS with NS background. And here, we conjecture that this Tst transformation in ADS with NS background would correspond to this TTbar, JTbar, or JJ bar deformations in the field theory. And again, the correspondence depend on the directions of your of the two U1s you choose to perform your Tst transformation. So before we were talking about TTbar, in that case, these two U1s correspond to the two null directions in ADS3. And if you choose one U1 in ADS3 and the other U1 in the internal direction, the conjecture is that it corresponds to this JT bar or TJ bar deformation. And if you choose it in both U1s in the internal direction, it could correspond to this JJ bar deformation. That's our conjecture. Now we'd like to give some evidence why this is true. So the first evidence comes from the spectrum. So one can, because we are performing TST on the string worksheet, this actually helps us to derive the spectrum very easily. So the main idea is the following. So by the TST transformation on the worksheet, people already found that after the TST, the string equation motion can be related to the equation motion before the TST by a field redefinition. And that means that solutions of the string in this new background can be obtained from the old solution by requiring that it satisfies some twisted boundary conditions. And this, the boundary condition actually depends on the deformation parameter as well as the two U1 direction, the momentum along these two U1 directions. And this process can be realized by some momentum-dependent spectral flow transformation. And by doing field redefinition and spectral flow, one can relate the new spectrum to the undeformed spectrum. So here's an example. Remember, we are considering long strings. That means that we consider strings with certain with a winding number along this ADS circle. So we consider ordinary ADS3, ordinary solutions of string equation motion on ADS3 background by introducing a winding. It's also a spectral flow transformation. And here is the Virasoro constraint after the spectral flow and before the spectral flow. They differ by this momentum times the winding. And similarly, the Virasoro constraint after this TST transformation can be obtained in a very similar way. It's just that this boundary condition will depend on the momentum. So we can collect all these terms. We can do both winding and this TST twisting. So in the end, this Virasoro constraint on the TST background with winding is then really can be related to the Virasoro constraint on ADS3 background without the winding in such a way. And so now what we want to have is the relation between the energy, or more precisely, the expectation value of the two momentums along the two U1s, two like directions. Here we denoted by P and P bar. So we want to have a relation between the winding strings on ADS3 and the winding strings on the the new background. So this by comparing the reversal constraint and considering the same internal excitations, and we will have this relation between the deformed background and the undeformed background. So this way, we will get this spectrum. So namely, this P again is the momentum along one U1 direction, and it will be mapped to the left moving energy in the dual field theory, and P bar is the right moving momentum on the worksheet, and it will be mapped to the right moving energy in the dual field theory. And we know that W is the winding parameter when it is chosen to be -1. The minus is due to our convention. The theory, this string is holographic due to the untwisted sector in the symmetric product, and for more general W is the twisted sector. So by observing this change of the momentum after this deformation, one can say this relation is precisely the relation of the spectrum of the TTbar spectrum. So this is one evidence that TST or this string background really correspond to this TTbar deformation. Any questions so far? Okay, then I will go to the third description. I'll describe the black strings. So as I mentioned, this is the geometry can also be obtained by this TST transformation. So before this deformation, let's consider the general Btc solutions. These are all locally ADS solutions parameterized by two parameters Tu and Tv. And when these are both real, they correspond to Btc black holes. And then when they are 0, that's massless Btc. And there are also contour defects when Tu, Tv are purely imaginary. And there is also a special value for these parameters so that the geometry is global ADS3. We can perform TST transformations to the entire class of such solutions. And along the TST is along this null direction U and the other null direction V. And finally, we get such a new background. It has, when lambda goes to 0, of course, we get back this old class of solutions. When lambda is non-zero, we see that asymptotically, namely, when R goes to infinity, the metric would become flat, asymptotically flat, while the dileton will become a linear dileton. So this geometry, the new geometry will interpolate ADS3 cross S, here is only ADS3 part. So interpolate ADS3 in the IR and flat space with linear dileton in the U way. So this general class of rotating black string solutions will correspond to this TTbar deformed field theory. And in particular, these solutions could correspond to finite temperature configuration of this TTbar deformation. So we'll show some of the details. With this solution, of course, it will be a solution to the supergravity equation of motion, because this solution is generated by the Tst transformation, and Tst is a useful solution generating technique in supergravity. So with this new solution, one can try to calculate all the properties, thermodynamic quantities of this black string. In particular, one can look at this when TU and TV are both real, they correspond to black strings, and the horizon is at this value 2 times TU times TV, and this horizon is actually independent of lambda. This is consistent with our intuition that this deformation is irrelevant and it should not affect IR physics. And when TU TV are 0, it has 0 temperature, and in the field theory set that that's the analog of this Riemann vacuum of the dual field theory. And we will also have this conical defect solutions, and later we'll also find a special value for TU and TVs such that the conical defect disappear, and we once again get a smooth solution, and that one would correspond to the NS vacuum of the dual field theory. And we can also observe from this expression that we want the dileton to be real, then the product of TU times TV would have an upper bound. And this upper bound, if you still remember, I mentioned in this TTbar deformation, the temperature, the product of the two temperatures also has an upper bound. And actually that's the same thing. So let's first look at the ground state. This is a smooth solution, and one can clearly see that when lambda equal to 0, this is nothing but global ADS. When lambda is non-zero, it interpolates between global ADS and flat space. And from here, one can see that lambda has a critical value. And this lambda is precisely this combination of this deformation parameter I mentioned before, and the critical value is a half. When lambda is greater than a half, the dileton will become complex. And when it's in between, then it's smooth and we have a real solution. One can also consider when lambda is less than 0, then this geometry will have a closed leg time-lag curve, and it will also have a curvature singularity at a certain point that is related to lambda. Okay, so here is some review of the holographic dictionary before the deformation. We know this class of Btc solutions. They correspond to finite temperature configurations of the set T. We know how to match the BTC entropy to a Carty formula from the field series set. But now we have the deformed deformed background. Then you could ask about the same thing. It's a black hole-like configuration. You can also calculate the entropy. Could that entropy can be expressed by entropy formula from the TTbar deformed theory. So when in the TTbar deformation, the entropy can be obtained easily using rewriting the Carty formula. And from the bulk, one can calculate the entropy, which is the area now. One can also calculate the energy and angular momentum. But in this gravity calculation, energy and angular momentum, you can basically you calculate these gravitational charges. And then after you do that, one can just rewrite the entropy, the black hole entropy, in terms of all the charges from the gravity calculation. By matching the corresponding charges, one can say the black hole entropy indeed can be reproduced by the entropy of this single trace TTbar deformation in the field theory. And one can also, as I mentioned, this upper bound of the temperature product can also be matched precisely. One can also consider this lambda negative situation. In that case, one can also find this upper bound of the energy by requiring the solution has a real deleton. And this upper bound also corresponds to the same upper bound that you will find in the TTbar deformation with this lambda less than 0. By the way, this lambda is just proportional to mu I mentioned before. Okay, so to summarize, we have a toy model for this non-asymptotically ADS holographic, and here I describe it in using 3 languages. One is TTbar deformation in the dual field theory, and the second language is using string worksheet, and the spectrum can be derived using the Tst transformation, field redefinition, and the spectral flow. And the geometry has the next feature that it is asymptotically flat. Hopefully that could tell us something about holography for asymptotically flat space. I also showed that there are 2 pieces of evidence for this deformation, for this holography. One is that the long string spectrum derived from string theory, and the TTbar deformation can be matched precisely. The other one is that by constructing the black string solutions using the TST techniques, one can show that the black hole entropy can be reproduced by the single trace TTbar deformation. And we also reproduce this critical value and critical energy for this TTbar deformation from the gravity set. So this is the TTbar, and similarly, one can also do a very similar construction, and as I mentioned before, if you do a TST using the two circles in ADS3, you get TTbar deformation. If you choose one circle in ADS3 and another circle in the internal direction, you will get a JT-bar deformation. And the JT-bar deformation will deform the three-dimensional geometry to the so-called warped ADS geometry, and this is relevant for the, it can be used as a very toy model for the current CFT correspondence. More generally, one can do this combined TT-bar, JT-bar, and TJ-bar deformation. So it's you can in this combined case you have 3 parameters, and this can be realized by 3 TST transformations using different circles. And one can also find that a similar story also works very nicely. So let's provide some more evidence that there's this connection between TST transformation and such irrelevant deformations in the field theory set. Okay, I'll stop here. Thank you.
Okay, thank you very much. Let's thank Wei again for the wonderful talk. Is there any question?
I actually have one question. So regarding this last slide about the generalization to JT and TJ, so the black strings are again like this kind of linear dilaton backgrounds, asymptotically?
Yeah, it has linear dilaton, but it also has, it's not flat spaced. It's not asymptotically flat.
What is it? It's warp CFT kind of. So it's non-relativistic.
It's non-relativistic also, yeah.
Right.
If you only have GT bar, then you have constant dilaton, and it's warped ADS. It's already non-relativistic. But if you turn everything on, you have basically both.
Right. And another question, what about the JJ bar? Can you include that as well in this case?
JJ bar only changes the internal directions. It's marginal in both both on the worksheet and also in the field series set. You will still get a CFT.
Also on the target space.
The target space, yeah, the target space is still ADS, but the internal manifold will change.
Right. Yeah. Thank you.
Any other question? So I have one question. So do you have some higher dimensional analogy of these relations, like ADS4, CFT3, and probably world volume theory and two brains?
That I don't know yet. Yeah, so this the field series set at the moment it depends on this symmetric product. The single trace deformation It depends on this symmetric product structure. But TST, in principle, one can do it in
right.
any dimensions. But I don't know whether it's related or how it is related to the deformations in the dual field theory.
Okay.
Another thing is that here in ADS3, the background field are NS, in like higher dimensional dualities. People more generally, usually people consider this R background.
Yes.
So I have one more question. So the deformation of spectrum, is it same as you have a single trace and a double trace? Do they also have same deformation of spectrum, or is there some difference?
So when W equals to 1, so we say this the spectrum derived from string has this parameter W.
Okay.
So when W equal to 1, this is precisely the double trace spectrum as well. But when W is more general, this corresponds to the twisted sector. Twisted sector.
So you mean depending on the W, deformation, I mean spectrum might be different from the double trace one. And then
it has this extra parameter.
Okay, thank you.
But it looks it's not unrelated.
Okay, any other question?
Can you generalize this to supersymmetric case?
Before the deformation, the theory has supersymmetry, but in general, TTbar deformation will break supersymmetries.
For the double trace or single trace, or either, both of them break the always, I mean, usually break the supersymmetry, or why is it broken? Or is there, can you explain a little bit more?
This in general, this from the field theory side, this if we consider TTbar, it breaks also conformal symmetries, and there are only two killing vectors in the theory.
But I'm just I mean, without any holography, just a quantum field theory formation, and if you ignore this holography and you just start from the some supersymmetric field theory, maybe it need not to be conformal, super conformal field theory, but just a super quantum field theory, then still it's usually broken, or or like is there some reason why it's broken? Like for example, conformal symmetry is broken because lambda is dimensionful, but supersymmetry, there's some fundamental reason.
That's the deformation is defined using the stress tensor, and this this is and it's this deformation operator, it's in general will not commute with the supercharges, right?
But maybe the question is like, I mean, is there a supersymmetric version of that deformation? So for example, you can think of like, I mean, the current multiplet, right? I mean, on the worksheet or target space, and just construct some generalization of this TTbar using the current multiplet, right? I mean, a supersymmetric version of that. Is there such a thing?
No, in my case, it's really non-supersymmetric. Yeah, there is a supersymmetric version, but still non-supersymmetric deformation. Does it break? I mean, of course, it's a non-trivial. I mean, usually it looks like broken, but if you see the spectrum, if every spectrum follow the one formula, then there will be the boson as fermion has same energy at each level. And
but if you, I mean, if the deformation is non-supersymmetric, then I mean, I don't think you can expect supersymmetry to be preserved, right?
I mean, but if you see the spectrum, no.
Well,
Okay.
I don't know.
I don't know if there. Yeah, there is a supersymmetric version of this.
Okay, is there any other question or? Kim Young, do you have something to say?
No, I guess I have to thank the Wei Song for a wonderful talk.
Okay.
Yeah.
So if there is no more question, then let's thank Wei again.
All right, thank you.
Thank you very much.
Thank you.